Welcome to Lesson 1D, Bulk Molecular Weight. We're going to talk about two more things related to ideal gas mixtures. The first is bulk molecular weight, and then we'll talk about how to manipulate these equations when we need other variables. Let me start by saying that in most applications, air is typically, when we're talking about air pollution, air is typically dominant. So we have mole fractions of air pollutants that are in the tens of parts per million or even less than that. So in that case, we can just use M of air, even though there's some other stuff in there. More generally, we must actually calculate what we're going to call the bulk or total molecular weight of the mixture of gases. I'll use both of these interchangeably, and we'll use the notation M sub T. So in other words, MT is approximately M air for some problems, but in the more general case, we have to calculate that. So let's define then MT, the molecular weight, is little mt over NT. So molecular weight is mass over number of moles. And remember, my capital M's have these pointy looking tops on them, whereas my little m has a rounded with a little thing on the side. Hopefully you'll be able to distinguish those. Please write carefully on your homeworks to distinguish those things. And so this is true for any ideal gas, so therefore it's true for a mixture of gases as well as the total. So this will manipulate is equal to the sum of all the masses of all the species over NT. And remember, J equal 1 to capital J. That's implied by that summation. And NT is the total number of moles of all species. We also know that NT is just a constant, so we can move inside the summation sign, the sigma. So we get capital MT is equal to sigma MJ over NT. And then we use the fact that MJ is equal to MJ NJ. That's kind of the same thing we had here, except we're applying it to one species. And then when we apply that, we can write this as sigma capital MJ NJ over NT. And this whole thing is in the sigma. And now hopefully you can recognize that NJ over NT, this is equal to YJ for species J, which is the mole fraction. And I just want to make a statement here is that you can get mixed up between N's and Y's and M's and all that, but once you start doing this enough, you'll remember these and it'll become very obvious to you what we're talking about. But remember, Y is the mole fraction. So finally, we get then that the bulk molecular weight or total molecular weight is sigma Yj capital MJ. That's our final equation for the molecular weight. So we'll call it the bulk molecular weight of a gas mixture. So let me do an example. So I picked simple natural gas. Again, this is similar to a previous problem that we did. 3 chemicals, methane, primarily 90% mole fraction, ethane, and propane, and calculate the bulk molecular weight. So I'll use this equation that I just derived here, and I need to find then the molecular weight of each of these elements. All the elements that I have, the only ones I have in this case are carbon and hydrogen. So there's this cool online periodic table at this website that I will now go to and show you. So let me go there. So it shows you the periodic chart, and you pick one of these elements like C, carbon, click on it, and you get all this information. The most important one for us right now is the molecular weight, which they call atomic mass in AMU, atomic mass units. But remember, that's the same as molecular weight in grams per mole or kilograms per kilomole. So this is the value that I just showed you for carbon. We do the same thing for hydrogen. And so now we have to calculate the molecular weight of each of these 3 molecules. So let me do the methane, and it is CH4. So the molecular weight of the methane is equal to, I'll put the carbons here and the hydrogens here. So it's 1 carbon times 12.0107. I'm going to keep all these significant digits. And then 4 H's, so 4 times 1.00794, and that's equal to 16.04246, and that's gram per mole or kilogram per kilomole, take your pick. So this would be the molecular weight of the methane. Now let's do that for the ethane and the propane, and we get these values for the ethane and the propane. And now we have to use our formula for MT, which is sigma yj mj, and we plug in our numbers, where the 0.9 comes from up here, 90% mole fraction, which means that Y of the methane is equal to 0.90, Y of the ethane is 0.08, and then propane is 0.02. So that's where I'm getting these numbers from. And then the molecular weights, of course, are from up here. And so when I put all this together in my calculator, I get that MT is 17.72565 gram per mole, or MT is approximately 17.73 to 4 significant digits, which is pretty appropriate for these. You can actually have more than that if you want, but 4 is definitely a good amount for molecular weights to use, since we typically round everything at the end to 3 digits in our final answer for other analyses. Okay, so finally I want to do some manipulations, and what I mean by that is that sometimes we have variables, certain variables like Y or mass fraction or mole fraction or number of moles, total number of moles. We have to manipulate some of these equations to get a desired variable that we're using in some analysis. So in this problem, the mass fraction of some species J is known, molecular weight is known, and the bulk molecular weight is known. But the analysis that we're undertaking here requires a mole fraction rather than a mass fraction. So we're going to have to derive an expression for mole fraction for this contaminant species J. So we'll start with the definition of mass fraction, which, because that's known, the mass fraction Fj, remember that was Fj, was Mj over Mt. And now let's do the same kind of thing we did before. I know that Mj is Nj times Mj by definition, and then Mt would be the sum of all the number of moles times its molecular weight. That would give me the total mass. And then I can multiply and divide by Nt, so Nj over Nt, Mj. So I divided by Nt, and now I divide by Nt on the bottom, sigma Nj over Nt, capital Mj. And notice that I could put Nt inside the sigma since it's a constant, so I didn't have to put that outside the sigma. And now I recognize this grouping is Yj, and so is this. So this gives us Yj Mj over sigma Yj Mj, and we just derived an expression for Mt, and it was exactly what I have on the bottom here. So that is Mt. That gives me Yj, capital Mj over capital Mt. So what I asked for was mole fraction for contaminant species J as a function of the given information. And so my final result, my answer, is Yj from this equation is equal, let me just rewrite this equation. Our final result was Fj equal Yj Mj over Mt. So just solve for Yj. Yj equal Fj Mt over Mj. And that's our final answer. So that's one way to do it, and that's just gives you some practice manipulating, what I call manipulating. Or if you're a little more clever, you might do it this way. Fj is Mj over Mt by definition. We start the same way, but now I recognize that this is Nj Mj, just like I had up here. But my denominator now, this is Mt, so Mt is Nt times Mt. And then this is my Yj. So I get Yj Mj over Mt, which is the same thing we had up here. And so that was a much easier way to find this answer, Mt over Mj. This agrees with what we had before, although it was much easier to do. And so you may not have been clever enough to figure that out. In fact, I wasn't clever enough to figure that out the first time. And then I thought, hey, this would be easier this time. So I just decided to show you both ways. And that's where I will stop. And you will have a quiz on this. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.